All right, so the only thing I really want to the only thing I really want to talk about today is Seiberg duality. So remember that yesterday we started mapping out the vacuum structure of super QCD. So I went through, after kind of defining it and writing down the D terms, et cetera, I went through a detailed discussion of what the classical and quantum moduli spaces were for all ranges, sorry, the classical moduli space for all ranges of NF and NC. And for NF less than NC, classically, it's just some of the gauge group is Higgs, and then you get you get an unbroken gauge group times some light scalar fields. For NF greater than or equal to NC, everything is lost generically, and the theory gets completely Higgs. That's the classical moduli space. And then we discovered that the quantum moduli space of NF less than NC was actually that there was none, because there was a dynamically generated superpotential which completely lifted all the classical vacua. So I didn't have a chance to talk about NF equals NC, and if I have time at the end of today's lecture, I'll do that. But what I'm really interested in now is the case that is NF greater than NC. And actually, so something interesting also happens at NF equals NC plus 1, but I'm not going to talk about that at all. That's something we can maybe postpone for the discussion section. What I'm really interested in today is I want to know what happens to super QCD when NF is greater than NC. And remember, so if we actually want the theory to be asymptotically free, I showed you yesterday, remember the one loop beta function is just 3NC minus NF. And I want that to be, this number to be positive so that the one loop beta function is negative. And so the only thing I'm really ever interested from now on is NF is less than 3 NC. But let me ask a question here. What if NF is just slightly less than 3 NC? What do I mean slightly less? These are generically integers. Let's say I take some kind of large n limit where I'm tuning both of these very large. What happens if I make NF then just a little bit less than NC? The ratio of these two things is, or the difference between these two things is small compared to either one of them. So this actually illustrates a very general phenomenon in gauge theories, which I want to talk about in some detail here. And so this is the idea of Banks-Zaks fixed point. All right, so this is, let me get away from, for the time being, let me actually completely get away from supersymmetric gauge theories. And what I'm going to say right now is true for non-supersymmetric gauge theories as well, and in fact was first discussed in that context. So let's imagine the following. So let me just write down the beta function for some gauge theory. All right, well, there's a one loop part, which goes as g cubed. And then there's a two loop part, which goes as g to the fifth, et cetera, et cetera, et cetera. OK, well, let's see. I know the one loop beta function, and let me use the particular example here of, actually, you generally don't need to, right? The one loop beta function, I guess I'll just write it down. Generally looks like this, right, where it's something times NC, some number, times the Casimir of the adjoint, minus something having to do with the matter. So generically, it's going to be some number times something order NC, minus some number times something order NF. So let's imagine I tune both of these. I take NC and NF to some range. Let's tune these to make this thing order 1. Right, so I'm adjusting NC and NF to make this thing order 1. The two-loop beta function for super QCD, I actually wrote it down. So let me just read this off. What I'm about to say, the explicit expression is true only for super QCD, but the same idea will hold no matter what I'm doing. So it's 4 NC minus 2 over NC NF minus 6 NC squared. Remember, this is some scheme-independent quantity. And if I take NF and I tune it to be very close to 3NC, and then I take a large N limit, what you can see here is, let's see, I'm going to get 12 minus 6. This is going to be order, it's going to be 6NC squared over this factor right there. But in terms of counting of NC, this two-loop beta function is going to be order NC squared. Again, I'm taking a large N limit, and I've tuned the number of flavors so that this thing is order 1. Yeah, this is the beta function for the physical gauge coupling. So this would
you just have to do hard work.
but it doesn't matter, right? Because this is scheme independent.
Can I read this off from NSVZ?
Yeah, if you calculated anomalous dimensions and stuff. All right, so what's the point? So, all right, let me just, I have a negative one-loop beta function and a positive two-loop beta function. This possibility was actually first pointed out by Gross and Wilczek that this could happen. Then Banks and Zaks considered this, this example. So let's see what happens if I just solve the beta function. Now, there's no reason a priori to trust that I can do this. We don't know if further corrections out here are going to be negligible or not. But let's just solve it and then see what happens. So if I solve for some G star where this beta function vanishes, what do you get? Well, let's see. You get, I can factor out a G cubed, and I get G squared star equals B1 over B2, which is something order 1 over order NC squared. This is order 1 over NC squared. And so what this tells me is now, all right, so then a parameter that'll look familiar to you because you've seen it in pretty much every other lecture except mine up until this point is the 't Hooft coupling, G squared N. This thing is, in a large N limit, perturbatively small. And so what I've demonstrated here is that the beta function in this large N limit actually has a fixed point that is perturbatively accessible. And in particular, you expect higher corrections. Because this is very small, you expect higher corrections. OK, they'll change the exact value of this fixed point, but you wouldn't expect them to completely remove it. So this is the phenomenon that was discovered by Banks and Zaks, that in a large N limit, you can have a fixed point to the beta function, which is actually perturbatively accessible. So said another way, if you're actually going to draw this picture, here's the gauge coupling. Here's the beta function. The two-loop beta function starts dominating very, very quickly, right? So you get something that just starts to go a little bit negative and then immediately jumps up. So you have some fixed point here, which is small. And generically, of course, you wouldn't expect this to happen. You don't know what's going on or exactly. You wouldn't expect to be able to just trust this two-loop thing. But what I've motivated here is that in fact you can trust it not to give you the exact value of the fixed point, but to see that a fixed point will exist and won't be destabilized by further corrections.
To trust that, you need to know how the B3, the higher loop beta functions, scale with NC. So if B3 goes with NC to the 4th, then I think you're in trouble.
Yeah, but I think generically you can show it's just another power of.
They keep going with NC squared.
Yeah, in this large one. Yeah. That is, there will be some scheme-independent parts to those higher. So in general, the coefficients to the higher beta functions will be scheme-dependent. But there'll be some parts that will be independent of scheme, for example, and you can show that those conspire to make everything work out. OK. So so good. So this is the idea of Banks and Zaks. You can have a perturbative fixed point. And you can see that although, yeah, I used the exact form of the beta function here for, or I should say these exact coefficients I used in super QCD. This type of scaling, NC squared, I can make beta, the one-loop beta function order 1 doesn't depend really at all on it being supersymmetric. I'll just change the exact numbers here for the beta functions in, let's say, non-supersymmetric QCD. with arbitrary NF and NC, and the same conclusion still applies. So this is a generic phenomenon in gauge theories. And one thing this tells you, which is perhaps surprising, or I think may have been surprising at the time, I don't know, I wasn't there, is that fixed points are in some sense a generic phenomenon in gauge theory, right? I think it was probably the conventional wisdom at some point that conformal field theories are kind of a very exotic, weird thing to have. You don't see them that much. But what this tells you is, as kind of a consequence of large N, conformal field theories, in fact, are a generic phenomenon anytime you're near the asymptotic freedom bound. And so we expect this to be true in super QCD as well. In fact, I showed you this for super QCD. And so what we expect is that for NF very, very close to 3NC, but just slightly below, we'll expect this theory to flow to some fixed point in the infrared. And one thing I should say, I'm just assuming straight off the bat here, is that whenever my beta function has a fixed point, the theory is actually conformal. That scale invariance somehow implies conformal invariance. And of course, this hasn't been proven, but it is generally the lore. This is an interesting question that I'm not going to have anything to say about. There's a paper by Polchinski you can check out if you're interested in that further. OK, great. So this is Banks-Zaks. And in particular, when I have some supersymmetric theory, what I'd expect down here at this fixed point is that I'll get something which has supersymmetry and conformal invariance. I'd expect a superconformal field theory. And that's what we're going to be talking about for the rest of today and tomorrow. So I figured this was a good point to review some basic facts about superconformal field theories. Maybe not review if you've never seen them before, but state some basic facts about superconformal field theories. So here's a review / intro, depending on who you are. Of superconformal field theories. And the whole point of this discussion was just to motivate that, yeah, they can exist. OK, so what is a superconformal field theory? It's just, let's just think about the symmetries of the field theory. Think about the generators. Well, so the superconformal algebra, superconformal superconformal. I'm going to write out the word superconformal. Algebra well, you do exactly what you always do. Let's say, well, we have the conformal algebra. And what is that? So the conformal algebra is your usual Poincare stuff augmented by two operators. So let me just write these things down. So here we have dilations, just scale transformations, or dilatations, if you like that. Just momentum, Lorentz rotations and boost, and these things over here, which are the special conformal transformations. It's some kind of inversion, which I won't get into the details of. All right, so these form a perfectly nice conformal algebra. And if you're familiar with conformal field theories, you've seen this before, and you check that this is closed, and you're great. But of course, to this mix, I'm adding supersymmetry. Which, in my n equals 1 case, is just generated by, I could write just Q alpha, but I'll write Q alpha dot. And of course, then I have to check that the algebra is closed, so I have to consider commutators and appropriate anti-commutators to check that I really have included everything. And the answer is this is not the whole story. I have other things. So plus anti-commutators. So I'll write anti because they're both. And what you get here is you actually get 3 new things which you're forced to have. You get what I'll call S, S bar, and R. S is just, let's see, is this, that's reasonably legible. Well, I'll move it up here. So again, being a little bit schematic here, S goes, I'll drop indices because I'm not going to be explicit. S shows up when I look at how the supercharges transform under the special conformal transformations. And R actually is a U1 that shows up if I look at the anti-commutator of Q and S. And of course, I could, we could write out exactly the superconformal algebra, but I won't need the precise details of it for anything I do. So I'll just let you look that up in the references. And for now, please trust me that that everything works out with these guys. So the point is that you actually have some extra stuff that shows up in commutators, including these additional supersymmetries, which are still fermionic operators, you can see just from this, and also a U1 current. I haven't showed you it's a U1, but it is. And in fact, so this algebra has a nice form. I can write this as a supergroup, SU22/1. So really all this means is I have some, well, I have some bosonic part which looks like SU22. I have a U1 over here, and then this slash just means I have some number of fermionic generators as well. So roughly speaking, I'm thinking of this as there's some bosonic part up here, some bosonic part over here, fermionic parts over here. These fermionic parts are my 2 supercharges, Q and S. This is a U1, and this is SU22. And in fact, if I write out the bosonic part, I can show the bosonic part here is equivalent to I can beat this into a form where it looks like SO4, 2 times U1, which is nice because this is the usual conformal group in 3 + 1 dimensions, and this is a U1. So what do we notice from this? Well, a couple things. Good. We have the conformal algebra, which is part of it. That's nice. We also have an R symmetry. Now, I told you what an R symmetry was in global supersymmetry, not superconformal. But there was no reason that R symmetry always had to be anomaly free. Right? An R symmetry is something that you can add to the supersymmetry algebra, but there's no reason that it has to be there. It has to be conserved. Right? And in fact, something that's very interesting, which Nadi will talk about a lot next week, is when you do and do not have an R symmetry. And there's certainly no reason to expect there to be one. And in particular, for example, the Wecht-Zumino model, we saw it's very easy to write down superpotentials which explicitly break the R symmetry. But what this tells you is that if you're superconformal, you must have an R symmetry. It is necessarily part of the superconformal algebra. So that's an interesting fact, and that's something that we'll use extensively. All right, other facts. So now you can start playing with representations of the superconformal algebra just like you do with the conformal algebra. You still have things like primary states, which are highest weight states. All this, a lot of the usual stuff that comes along with being conformal is, of course, in superconformal. And it turns out, again, now I'm just kind of stating facts. I'm not going to prove these. So unitarity, that is, as always, requiring that your theory have positive norms, gives you actually a bound on dimensions of operators. On the dimensions of gauge invariant operators. And it turns out that the scaling dimension of any gauge invariant operator, that is the dimension given by what happens when I hit that with the D, has always got to be greater than or equal to 1. And this is saturated for free scalar operators. And you can see this if you play around, you put some appropriate generators in front of a state, you take the absolute square, you use commutators to get the scaling dimension out, and then you show that you get some kind of bound. The positive norm thing gives you some kind of bound. And again, it's not too hard to show, but it's more than I want to do now. This is also true in conformal theories. Yeah, that's right. Yeah, so I'm sorry, that was what I meant when I did that segue about everything you have with the conformal group. What I should have said is including this. Yeah, so this is just true about, there's nothing special about supersymmetry here. OK, but what is true for just the superconformal group is that there's a relationship between dimensions and R charges. So similarly, you can show that unitarity gives you a relationship, a bound between dimensions and R charges. And it's the same sort of story. The R charge shows up in QS. You put this in, you look at the absolute square of some state with these operators, and you get a bound on the R charge. And it turns out that, so I should say, there's a relationship between dimension and R charge and what it is that the dimension of, again, any gauge invariant operator has to be greater than or equal to 3/2 times the R charge of this operator. And I've put an absolute value sign around this because whether this is positive or negative will depend on whether it's chiral or anti-chiral. So this thing here is saturated for chiral primary operators. So again, if you're not very familiar with the superconformal algebra, the primary operators are some highest or lowest weight states, whatever you want to call them, and this is saturated for those operators. Okay, so the point is that if I have a chiral primary, I can just replace this with an equality, and then the dimension and the R charge are one and the same. Right? So if I know the R charge, I know the dimension. Let's see, was there anything else I wanted to say? All right, so let me use this to do something a tiny bit specious. All right. So let's say I have some chiral primary. All right, so for a chiral primary, let's see the dimension. So let's say, let me indicate, so I'll write, I'm going to use some abbreviation where I abbreviate the dimension of operator I by delta I. Similarly for the R charge. Right, this is not true just for a chiral primary. I'm making this true all the time. And then from this I see, OK, well, look, the exact scaling dimension is 3/2 times the R charge. But if I write the scaling dimension as 1 plus the anomalous dimension over 2, what you can see from here is that the anomalous dimensions are just 3r minus 2. OK, so what does this mean? Well, here's where it gets a tiny bit specious, but I'm going to use this to just motivate something. Is let's look at the numerator of NSVZ. Remember, we had the NSVZ beta function in supersymmetric supersymmetric gauge theories, and one thing I said is, well, maybe the numerator can be 0. So what I want to show you is that in a slightly iffy way, I can use this to show that. So the numerator, if you remember, let me just write it down, looked like this. It was the Casimir of the adjoint plus, so here's the one loop part. Oh, whoops, minus. Here's the one loop part right there. And then to incorporate the wave function renormalization, I put the anomalous dimensions in right there. Make sure I got that. Great. Cool. So let me, and this is the slightly iffy part, let me just feed these into here. I should say the slightly iffy part here is that really I should only do this for gauge invariant operators. And the kind of natural thing to sum over here are the degrees of freedom I put in the field theory, in the weakly coupled variables. Let me not worry about that and then just kind of go with this, and you'll see where this is going. So all right, so if I plug in these anomalous dimensions, what do I get? Well, let's see, 3r minus 2, get minus 3 minus 3r. Great. And now, of course, I can rewrite that. So let me factor out a 3 and move that minus sign through. Whoops, minus 1 for the numerator. All right, so what does this look like? Why is this at all interesting? Because this thing here is precisely the anomaly in the U1 R symmetry. Right? Remember that we had the anomaly of any U1 current was the charge of whatever field times its Casimir in whatever representation it was in. So here I have the anomaly from the gauginos, which are in the adjoint representation. That's what my T of G means. Then I have all the matter in the theory. The superfields have charges Ri, but the thing that I'm concerned with this anomaly are the fermionic components. And those have charge R minus 1. So this is exactly this thing right here is the U1R anomaly. And what this is meant to motivate is that if I'm at a fixed point, if the numerator of the NSVZ vanishes, then this anomaly must vanish as well. So NSVZ having the NSVZ beta function equals 0 means that the U1R current is anomaly free. Which was, oh, did I precisely erase the thing I wanted? Yeah. This was, remember, this is something I said before, which is that in the superconformal algebra, there was a U1R current. This is another way of seeing that. So this is the U1 inside SU22/1. Right. Good. OK. So great. So there are some facts about some superconformal algebras. So this is all kind of secondary, though, to actually asking if there are superconformal algebras around. Yeah.
When you replace the dimension of the operator with 1 plus the anomalous dimension,
yeah,
that's not true for a general chiral primary, but it is true for the quark fields that you.
Yeah. Right. Good. That's right.
Is that right?
Yes.
Okay.
So great. So now that I've reviewed these generalities, the question I want to ask is, well, when do we expect this to happen? Well, I already argued that in supersymmetric QCD, for NF less than 3/2 NC, or NF very near 3/2 NC, we'd expect to get some kind of fixed point. So what I want to do now is I want to review Seiberg's argument that actually this is a very general feature of super QCD. And in fact, we expect this to be true not just for large n, but in fact for finite n and a whole range of NF and NC. And this is kind of a remarkable result. All right, so let me go back to just writing down. Let me remind you what super QCD was. I think that's all I wanted to say about that. Yeah, great. All right, so here's super QCD. Again, as usual, I'm going to stick with gauge group SUNC, although that really doesn't matter for what a lot of what I'm about to say. I've got NF quarks and NF antiquarks. These guys transform into fundamental, and the Q tildes transform into anti-fundamental. And let me write down again the global symmetries of the theory. So I had SUNF times SUNF flavor symmetry. Really, I have a UNF flavor symmetry on either side. I can split each of those UNs into, or UNFs into SUNF times U1. One of those U1s, the axial will be anomalous, so I won't write it down. We do have a U1 baryon, though, and a U1R. All right, so those are the global symmetries of super QCD. And let me just write down all the charges here. These R charges are something that we wrote down yesterday. Remember, by requiring that the R symmetry be anomaly free. So if you solve, so where do these come from? These come from solving that the R anomaly equals 0. OK, so Seiberg's claim is that we know that this should flow to a conformal theory right below 3NC, and NF equals 3NC. The claim, though, is that even further below that, it'll flow to an interacting conformal fixed point. So if I had to write down what this theory looked like in terms of NF and NC right now, and let me not take NC too low. I don't want to get into the NF less than NC region. So if I do a little number line thing here, right now, what this theory looks like is here it's for NF greater than 3NC, it's IR free. For NF less than 3NC, we know it's asymptotically free. And in a little window over here, there's no precise way to do this. Not only is it asymptotically free, but I argued it flowed to an interacting conformal phase. All right. So let's assume that this conformal phase extends out further. When would we possibly run into a problem here? OK. Well, it's pretty easy to see where a problem might set in. So what problems could I have with superconformality? Well, for one, I could violate a bound. So let me write down kind of a natural gauge invariant operator here, which is the meson I get by contracting the color indices of these two quarks. So let me look at the dimension of the following gauge invariant operator. All right, it's easy enough to do. I can just add these two, or actually even better, let me look at the R chart. Well, it doesn't really matter. Yeah, whatever. 3/2 times the R charge of these two operators. Well, here are the R charges. So 3/2 times 2 times 1 minus NF over NC 3 minus 1 over NC over NF. And you can see that, let me just take, let's see when this could be a problem. When would this be equal to 1? Well, it's equal to 1 exactly when NF equals 3/2 NC, which is easy enough to check. And in fact, it's only going to get worse below that, right? Below NF equals 3/2 NC, when NF is less than 3/2 NC, this thing is going to be less than 1. Right? So there's a problem with the theory being superconformal with this bound when NF is less than 3/2 NC. All right. So what could you possibly say here? Well, one thing, a conjecture, is that whenever this happens in a superconformal field theory, well, this is usually going to happen at very, very strong coupling. In particular, we're far away from this point over here. And so when you're far away from strong coupling, you have the possibility of accidental symmetries that you could not have seen from a weakly coupled ultraviolet description entering into the theory. And I'll show you that this is actually a very, according to Seiberg anyway, a very a common thing. So one possibility is that an accidental symmetry comes along and takes this operator, which was perfectly nice over here, and in fact free, right? This is the dimension of this being a free operator. An accidental symmetry comes in below this and makes this operator decouple from the theory. In fact, Seiberg's claim is even more dramatic. Seiberg claims that below NF equals 3/2 NC, not only is this operator free, but in fact the whole theory is correctly described by a free field theory. All right, so Seiberg's claim is that below here, the correct physics is described by a free field theory. Theory is free below NF equals 3/2 NC. And so what I'm going to do is I'm going to write down his proposed, so we have a very strongly coupled description over here at NF equals 3/2 NC. The claim is the theory is free. It'd be nice to write down a theory that you could actually see was free in this regime. So let me do that. Said another way, the claim is that in this regime, there is a weakly coupled, let's say NF is just a bit above 3/2 NC. There's a weakly coupled field theory I can use to describe the right degrees of freedom. So let me call this theory the electric theory. And let me call this one I'm about to write down the magnetic theory, and you'll see why I motivated these names in a little bit. So the claim is that the correct theory over here is an SU NF minus NC gauge theory. Actually, let me give myself a little bit more room. But of course, one thing has to be true. In order to describe the same physics, the global symmetries should match, so I shouldn't have any different global symmetries. And the field content of this putative theory is that I have still some quarks. In fact, NF quarks Q in the fundamental, NF Q twiddles in the anti-fundamental. At the moment, I'm just kind of writing this down, and you'll see why this is useful in just a second. And the global symmetries here Again, let me just write them down, and then I'll motivate why they're useful. What do I want to do? Oh, and there's something else that is absolutely crucial to this whole story, which is that there are NF squared mesons, or singlets in this case, sorry. There are NF squared fields which are singlets under the gauge group. So let me write down these guys. So I'll finish this and then I'll explain where it comes from. So this U1 baryon I'm going to take to be NC over NF minus NC. U1 baryon for the Q tildes will be minus NC. That'll be 0. And then my R charges, let me take to be this. And for right now, this seems just like a crazy assortment of crap. But I promise it's not. So what's one reason for believing this might be at least the right degrees of freedom at all? Well, one thing you can see, let's check where this theory becomes asymptotically free. All right, so what's the one loop beta function for this theory? Let me call that B dual. All right, well, that's easy enough to check. It's just 3 times what's NC for this theory, which is NF minus NC in terms of the old theory, minus NF. Notice that these new singlets don't appear in here because they're singlets. So what is this? This is 2NF minus 3NC. This theory is asymptotically free for NF is greater than three halves NC. This is where it's asymptotically free. So we expect this theory to be infrared free precisely below this point right here. All right, so that's one check, that this theory, if this has any hope of even being the right degrees of freedom, it actually is an infrared free theory below where it's supposed to be. Seiberg's claim is a lot more dramatic than that, though. It's that actually in between 3 halves NC and 3 NC, so if we were going to draw this similar phase diagram for this theory, well, phase diagram is a horrible abuse of words, but let me just write it. Here's 3 halves NC. Over here, this theory is asymptotically free. And in fact, exactly by the same argument we used for the original theory up here, we can argue that it flows to some kind of fixed point right about there. And it's IR free over here. And if you notice, there is an intersection between these two lines. For NF below 3NC over here and above 3 halves NC over here, both theories are asymptotically free. And in fact, Seiberg's claim is that they flow to the same fixed point in the infrared.
One thing I'm wondering about, for your SUNF column there, you've got a fundamental bar and then a fundamental there.
Yeah.
What is that? Can you just
I'm going to get to that
Okay.
in just a second. So one thing I can say here, okay, one of the reasons these charges come in, I'll answer this question now. One of the reasons I wrote these charges as I did, in particular these global SUNF charges, is I'm thinking of these singlets over here as what this composite operator gets mapped to. So what looks like a composite in the electric theory, as you flow down, the claim is that in some sense, this is a little bit iffy, but roughly speaking, this gets replaced by a singlet over here. And in order to have the same global charges, this needs to be charged under, it needs to be a fundamental under this SUNF and an anti-fundamental under this SUNF. So what I'm going to put in is I'm going to put in quarks. Essentially, I just posit these as the representations for those guys and then check that this works. But the utility here is I can now form a gauge invariant by contracting this with, sorry, not a gauge invariant, an SUNF times SUNF invariant, by contracting this singlet field with these two over here. Right? So I put this in the anti-fundamental to make sure that I can contract it with this flavor index over here and create an SUNF singlet. All right, so that's the reason that comes in. But again, at some level, I've just kind of written this down, and now I'm going to check that it's the correct thing. Right? There's no, and I think this is important to say, there's no sense in which you derive this theory from the above. You just sort of write it down, especially if you're Seiberg, and then you check that it satisfies a number of consistency conditions, which is exactly what I'm going to do right now. Okay? So if you want to think about this purely at the level of it's something I wrote down, that's great. And now I'm going to check that this thing actually satisfies a number of interesting properties. All right, so the claim is that these two theories, the electric theory and the magnetic theory, flow to the same fixed point in between 3NC and 3/2 NC. And let me draw this as one unified picture. So the claim is that SQCD does the following. Here's 3NC. Here's 3/2 NC. The theory is IR free over here in the original description, in the electric description. In fact, let me not say IR free. Let me say free electric. Below 3/2 NC, the theory is what's called free magnetic. Why? Because that's when I claim the correct description is this theory, the magnetic theory, and that description is IR free. And in between is what's called the conformal window, when both theories are asymptotically free. And what I'm about to demonstrate evidence for is that both these, in fact, flow to the same fixed point in the infrared. So said another way, and I kind of can't say this too many ways. Notice over here, near 3NC, my original description is very weakly coupled. Right? That's when we had this Banks-Zaks limit, when the perturbative fixed point was right there. So as I flow down here, or as I adjust the number of flavors as I go down here, the theory is going to become more and more strongly coupled at a fixed point. But over here, the magnetic theory that I've written down is just near its Banks-Zaks fixed point and is very weakly coupled. Okay? So if these two theories, the reason that this is often called electric-magnetic duality is because when one theory is very strongly coupled, the other theory is very weakly coupled. Right? Now, of course, there's a huge regime here where they're both strongly coupled. But certainly near the ends over here, this magnetic theory is a good description. I can identify weakly coupled degrees of freedom. And certainly near 3/2 NC, the electric theory, I can identify weakly coupled degrees of freedom. All right, so that's one of the reasons this is called electric-magnetic. And what this is meant to illustrate is that over here, the best description to use is the electric description. And over here, the best description to use is the magnetic description. But what is the evidence? I mean, so far I've told you no reason at all to believe that these flow to the same theory in the infrared. So the claim, Seiberg's claim, is electric and magnetic theories flow to the same fixed point in the IR. And I think this is, again, an important point. In the ultraviolet, these theories are different. They are not the same. They have different degrees of freedom. You can see it right there. The claim is that as I let these flow down to the infrared, these two theories exist in some kind of universality class where they have the same infrared fixed point. Okay? So the claim is not that these two theories are always equivalent. That's a lie. It's just simply not true. But the claim is that in the infrared, they flow to the same fixed point. And so what's the evidence? Okay, so let me run down a bunch of checks. So this is a very non-trivial claim, right, that I've written down. Two theories which flow to something which has non-trivial dynamics in the infrared. All right, so the biggest piece of evidence and I'll write down several of them. A 't Hooft anomaly match. All right, so what do I mean by this? The global symmetries, as I mentioned before, if I want these two theories to be the same at all, the global symmetries have to be the same. Right? The global symmetries are physical symmetries of the theory. Global symmetries better be the same between the two. And in particular, 't Hooft argued that I can compute triangle diagrams with 3 global anomalies in them in the ultraviolet and trust that the answer I get remains the same even in a strongly coupled infrared regime where I can't identify the degrees of freedom, which will generally be true here. Right? I've written down ultraviolet degrees of freedom here. In the infrared, this theory is conformal. I have no idea what the degrees of freedom are. Right? But 't Hooft, what I'm about to show you is that 't Hooft argued that I can compute global anomalies in a weakly coupled description and trust that whatever that number is I get, which is something that just depends on the global symmetry, which is a physical symmetry of the theory, should be the same even in the infrared. All right, so what's the argument for this? So 't Hooft says, global anomalies. So if I think of a triangle diagram with 3 global currents, these global anomalies e.g., so I'll write, well, the anomaly in UNR cubed here, just for example, should be the same in the ultraviolet as they are in the infrared. And so a check of these two theories is that if I compute the global anomalies in one and then the global anomalies in the other, I get exactly the same answer. If I don't, I haven't written down the right thing. So the argument for this, I'll just say it briefly, is to do the following. So take these global anomalies and gauge them. Just turn them into gauge anomalies. Right? That's a sick theory. Right? You have something that's now explicitly anomalous. But one thing you're free to do is throw in a weakly coupled, just a set of spectator fermions, which couple to these gauge currents, which have, you can just kind of dial the coupling to be whatever you want. And in fact, and then you can adjust the representations, et cetera, of these fermions to exactly cancel off these global anomalies. So then what you do is you let the theory flow down to the infrared. You're free to dial these fermions, so then you just dial them away at the end. Well, the theory stayed gauge anomaly free with respect to these things that you turned into gauge anomalies. Now the global anomalies at the end of the day in the infrared, you've just subtracted off whatever components those spectator fermions added. The global anomalies should be the same. So 't Hooft originally wrote this down, of course, not for some crazy supersymmetric theory, but he was just looking for an infrared description of QCD. But the argument is still the same, no matter what. Right? The global anomalies should be the same in the ultraviolet as they are in the infrared. And what's remarkable about that is that I can compute these global anomalies, which I'll do an example of in just a second, in terms of a weakly coupled description, like I've written down here. It's important to emphasize that these are both weakly coupled descriptions, and still trust that whatever numbers I get for the global anomalies, which are physical symmetries of the theory, not like a gauge symmetry, which is just a redundancy, whatever things I get for the global anomalies had better be the same. Otherwise, there's no way these two theories could be the same in the infrared. So let's compute. Let me do an example. So you can check all of these. And they all work. But the easiest one to do, or my favorite one to do, so So I want to check the following global anomaly. I want to put an R current here, and then 2 gravitons. So what this is computing is a U1R anomaly. Yeah, well, I'll write it like this. All right, so let's do this in the electric theory. Now I could do any combination of these global symmetries as I want. Of course, if I only put in one of any given non-abelian thing, that's trivially just going to drop out. But there are lots more non-trivial ones to check. So let me just do U1R. OK, so what do I have? Well, I have gauginos, and I have my quarks. Right? These are the fermions that I have in the theory. So let me compute what this anomaly is. In the electric theory. All right, let's see. The gauginos have R charge 1, and they're in the adjoint, so there's an NC squared minus 1 dimensional representation of them. So these guys are going to compute NC squared minus 1. This is just from the gauginos. They have R charge 1. These gravitons here basically don't affect them at all. So when you put a gaugino around there, when you contract all the gauge indices, you just get the dimension of the representation. And then I have some flavors. I have NF of them in NC dimensional representations. And in fact, let's see, there's my R charge. Here I'm going to put the R charge minus 1 because it's the R charge of the fermion component of the superfield, not the scalar component, which is what that R charge is. So I get minus NC over NF. And now it's easy enough to see that the total anomaly here is minus NC squared minus 1. All right, so let's do it in the magnetic theory just as a check. All right, so it's slightly more non-trivial here, but it's still not too bad. The gauginos are going to give me the new rank of the gauge group squared minus 1. So in the magnetic theory, that's NF minus NC squared minus 1. And then what do I have? I have these guys and these guys. So from my singlets, all right, let's just write all this down. From the mesons, all right, they're NF squared of them. They're trivial in the gauge group. They're singlets, so they're in a one-dimensional representation. And then the R charge is that thing minus 1. So it's 1 minus 2 NC over NF. And then I have the dual quarks, which are NF of them in NF minus NC, right there in the fundamental. This is the dimension of their representation. And their R charge is NC over NF minus 1. So I'm not going to do the algebra for you, even though that would be great. But you can check that, in fact, this equals precisely minus NC squared minus 1. And so you can see where some of these charges came from now, right? Precisely, I put these charges in to make sure that the global anomalies match up. And in fact, you can check that any global anomaly you write down here is always going to work. And this is a highly non-trivial check of Seiberg duality.
I guess these R charges are only really fixed when you write down the super.
So the R charges for these are fixed by anomaly freedom. This R charge is only fixed by the superpotential.
That's also fixed if you insist it's Q.
Yeah, that's right. So one thing you could do here, and this is actually something I'll talk about in just a second. So Dave's question was, these R charges, are they only fixed once we write down a superpotential? I haven't written down a superpotential, but I'm about to argue that I absolutely have to in order to get these to agree. If I just ignored that right there, these R charges would be fixed by anomaly freedom. This came seemingly out of nowhere, but the reason I wrote it down is because I'll need a superpotential in this theory, and this R charge is exactly what I'd get from the superpotential I need to write down. OK, so you can see already that even in this example, these conspire in a very non-trivial way to give you the right anomalies. The fact that the global anomalies match up is a highly non-trivial check that you've identified to two good descriptions. OK, what else can I say? What are other checks? Don't want to erase any of this, but I'm going to erase up here. OK, so the most trivial check I could have written is, are the degrees of freedom the same in these theories? And naively not. I mean, let's just check the gauge invariance. Here I have more stuff I can write down, right? I threw in a bunch of singlets. One of the reasons I assigned, however, so one thing you want to do is you want to map the gauge invariant operators in one theory to the gauge invariant operators in the other. So one thing you can see, for example, is the reason I assigned these baryon charges here is so that when I anti-symmetrize these quarks and all of their NF minus NC color indices, I get something that has charge NC, baryon charge NC, which is exactly the same thing I'd get from a baryon from the Qs up here. Same deal with the Q tildes. But I have too many degrees of freedom because I have singlets over here. So check 2, degrees of freedom, fails. But there's something I can do to rectify it. Degrees of freedom. It fails unless you include a superpotential for the dual theory, which I'll call W dual, which looks like this. And in fact, let me be very explicit here. Let me write down flavor indices. Like that. So I couple these singlets. I couple these singlets. I contract them with the dual quarks by contracting flavor indices. So this was the answer to your question. That's why I picked these dual quarks to be in anti-fundamental and fundamental representations of SUNF to make sure I could write this thing down as a completely neutral superpotential. So you can check, by the way, that this has R charge 2, and this is where the R charge of this meson came from, is the R charges of these quarks are fixed by anomaly freedom, and then in order for this to be a superpotential, it has to have R charge 2, and so then the R charge of this meson is fixed. Now you could ask, what if I didn't write this superpotential down? Let's say these mesons are just free fields, they're kind of flying around. It's easy to see that this superpotential is a relevant operator. So for example, just above NF equals 3 halves NC, if this thing is free, it'll have dimension 1. These guys, you can check, will have dimension slightly less than 2. So the superpotential has dimension less than 3. OK, that may sound weird, because normally you'd think I'd want to say 4 there. But for a superpotential, the criterion is that it has dimension less than 3, because the thing that goes into the scalar potential is the derivative of this squared. So this superpotential is a relevant operator if these m's are just initially decoupled. So this will flow to some fixed point where this actually where this is the superpotential. All right, so degrees of freedom naively work. Other checks. Is the dual of the dual the original theory? So one thing you can do, the prescription for duality now is very simple in Super QCD. Given anything you had that you could construct a meson out of, Q tilde, you write down a bunch of singlets. And then you couple those to the new degrees of freedom. OK, so is the dual of the dual equal to electric? All right, so let me just kind of go through the schematics of this. So what would the dual of the magnetic theory be by Seiberg's prescription? All right, so here we have the magnetic theory. It had Q. Let me write that even bigger. Q tilde, and M, and a superpotential MQ tilde. To dualize this, what do? Well, the claim, so I introduce new dual quarks. So, I don't know, what would you call this? Ultramagnetic? I believe the ultramagnetic MCs were Cool Keith's original rap group. Cool Keith is great. So if you do the dual of these quarks, R tilde, all right, so you get some dual quarks over here. These singlets just come along for the ride, so let me call them M tilde. But now I can construct a composite operator out of these two, which will become another singlet, or another set of singlets over here, which I'll call N. All right, so all I did was I kept these, I introduced some dual quarks, I kept the singlets over here, but I constructed a composite out of these that I reinterpreted as a singlet right there. And then the new superpotential, so let's see, if I just replace these by their composite, and then I add a dual superpotential of this form, you can see what this does is this is a mass term for m and n. And when I integrate out n, I just set m equal to this composite, and m goes to 0. Right, so what I do is I recover a theory when I integrate out these fields. So I should say integrate out m, and you get back to the original electric theory. Now there's a slight subtlety with the coefficients of these and a relative sign that I'm not going to get into right now. But at least the point remains the same, is that in writing the dual of this dual superpotential, that acts like a mass term for these two fields, which can then be integrated out. OK, so the final check is I can just do some interesting deformations to both theories and see what I get. So for example, let me ask the following question. What happens if I introduce a mass term to the original electric theory? OK, so I have two things. So in the electric theory, let's say I introduce a mass term. So write a mass term for one of the flavors, just one of the flavors. M Q Q tilde for one flavor. Well, what does this do? I can integrate this flavor out. It doesn't change the gauge group at all. I'm not giving it a VEV. I'm just integrating it out. So this takes, so what this does is this takes SU and C with NF flavors to SUNC with NF minus 1 flavors. I just integrate the flavor out of the theory. That's all I do. OK, so what I want to see is I want to see that this does exactly what's expected in the magnetic theory. So in the magnetic theory, what should this do? Well, I can see what the dual superpotential will be here. I just replace this with its singlet. So maybe I should introduce indices here. NF, NF, just to indicate that I'm only doing this for one flavor. M, NF, NF, plus the Seiberg dual superpotential I wrote up there, where this couples to all the Q's. And you can see what I need to do now. So this is exactly the same theory I wrote down before. Over there, it's an SU NF minus NC gauge theory with NF flavors and some singlets. And in fact, so what does this do? I can integrate out this one particular meson field. That meson is going to give a VEV, right? If I integrate out the NF-NF meson, it's going to give a VEV to these quarks, to this flavor, which will then Higgs the theory, right? So it's going to give a VEV to this one meson constructed out of the QQ tildes. It's going to Higgs the theory, so I'll lose one flavor and one color. So if I integrate out M and F, this takes, again, this guy and makes it non-zero, gives this thing a Vev, which Higgs is the theory. You can check the counting of the singlets as well, that this removes some singlets, and in fact it does. So what does this do? This Higgs is to SU, I just dropped that by 1. And it has 1 fewer flavors. And again, let me not write down the singlets for right now. You can check that those actually work out as well. Is this what you'd expect? It's exactly what you'd expect from the dual of this endpoint over here. Right? If I take this theory and I look at this guy as a comparison, NF minus 1 minus NC gets the ranks right, and the number of flavors doesn't change as well. So the idea is that a mass term in one theory, integrating out a flavor in one theory, is like Higgsing the dual theory. And in fact, that's also true if I started by giving this operator a Vev. If I gave QQ tilde a Vev, if I wanted to Higgs the electric theory, if you go through the same sort of argument, you can then argue that that actually is the same as adding a mass to a flavor in the magnetic theory. So this is another non-trivial check that you can actually do this procedure and get the same endpoint that you expect by duality. So the entire point of all this stuff is just that the phase, I've never written on this board before. The phase diagram for super QCD is this thing I erased. Which is that there's a conformal window of fixed points between 3NC and 3/2 NC. And in fact, so you may say, OK, great, there's super QCD. So is this just true for super QCD, or is this true for something else? And in fact, this kind of duality has now been done for a lot of different kinds of theories. It's by no means something you can always do. It's a highly non-trivial thing to write down the dual of some theory. But for example, I can do super QCD with different gauge groups. I can do SO and SP. I can do, they're all variants of super QCD, kind of with different matter added in. I can add in, an adjoint and look at the dual of that theory with some appropriate superpotential. I can even look at chiral theories and write down duals for some of these, which is a very interesting thing to do, right? Theories which have no Q's, but only Q tildes. Duals for some of these theories are known. In every case, there's not kind of a direct way of just sort of automatically writing down the dual, but a lot of this stuff is now known. The best source, if you want to look at a paper that, kind of in the heyday of all this, just took every theory they could think of and wrote down the dual for it, is Intriligator, Lee, and Strassler. They have some paper where I think they write down literally the duals of like 40 theories. And you can just kind of go through and look at all the examples. So this is not a phenomenon that is just for super QCD. This is the kind of thing that you can actually do for a wide class of gauge theories. And in particular, one lesson to be learned from this is that the existence of interacting conformal fixed points is something that is not that rare of a thing. And it's the kind of thing we see a lot of as we study more and more gauge theories. So what I'm going to do tomorrow is I'm going to talk more about superconformal field theories in general and talk about some exact results we can prove just for a very general superconformal field theory. All right, so I'll stop there for today.
Any superconformal questions, Brian? Dual questions?
And we have a discussion section later today, too, right?
We do.
Okay.
Yeah, we have a discussion session at 5. OK, let's thank Brian again.
Thanks.